In the last few videos, we've examined different orders of reaction and what the integrated rate laws look like for those orders. And implicitly, we were treating reactions that look something like this. And I realize that this is a pretty abstract way to write a reaction, but we're starting with one reactant and it goes to products. And there was some reasoning for that, and that is that for these cases we can explicitly integrate the differential rate law and come up with a closed expression for that. What I want to consider this time is some of the challenges that we face if we had, for example, two reactants reacting together to form products. Now, there's a couple of things I'm going to do to make our life a little simpler. One is I'm going to assume that these two come together in a 1-to-1 ratio. That is to say their stoichiometric coefficients are both 1, so we don't have to worry about that part. The other thing I'm going to assume is if we write down the rate law, okay, the rate law is either equal to the change in A with respect to time or the change in B with respect to time, and these should be equivalent because they're reacting in a 1-to-1 ratio, and that we're going to assume that this is first order in A and in B, so the overall order of this reaction is order 2. But that doesn't mean that it necessarily will result in a similar expression to the one that we've had before for a second order reaction. Right, we're also going to assume that we start off with these concentrations for our two reactants, but I'm going to further make the assumption that these are not equal to each other. That is to say, we're starting off with different amounts of them, even though they're combining in a 1-to-1 ratio. Now, the reason for this is a little subtle, but I'll simply say that if I had them both at the same concentration to begin with, that in effect I've reduced the number of variables in this equation by 1 because they're both changing exactly the same, and they're linked to one another via this balanced chemical equation up here. So in fact I would only have one rate equation, not two, to worry about, and I could easily derive the time dependence of one from the other. Okay, so we're going to assume that these are different from one another and that they follow this particular rate law. So how would we go about figuring this out? Well, first of all, I want to note that if I'm interested in the concentration of A at some later time t, that it's going to be equal to its initial value minus some value that represents the extent of the reaction. So we'll just use that same variable that we've used before, the Greek letter xi. I'm going to have the same expression, though, if I talk about B. And it's going to be the same amount of extent of reactions. In other words, these two things are the same. Now, why is that? Well, these things are reacting in a 1-to-1 ratio. So if it was A plus 2B, then I'd have to double C that's being subtracted from the initial B. But since they're the same, it turns out if I solve for Xi in both cases, so for this first case I'd have Xi over on the left-hand side and this going back over to the right-hand side, I would have Xi is equal to A0 minus A as a function of temperature. And similarly for B, I would get the same kind of expression. But since this extent of reaction is the same in both cases, I can now use this to derive an equation for this time dependence in terms of this one. Now let me step back for a second and explain why I care about that. All right, if I simply write down this rate equation that I've got here, and both of these are a function of time, it's going to become much more difficult for me to integrate that directly because I've got two things here that are related to time and they're changing with time. So without having foreknowledge of what exactly their dependence on time is, it's going to become very difficult to integrate this equation. This is actually very similar to the problem that we have when we're trying to integrate, for a thermodynamic process, if we want to integrate from state 1 to state 2 of the change in heat or the change in work. Since it's a path function, it's going to depend on what path we take to go from one to the other. This is not quite exactly like that, but we don't know the path that it's on, so we can't evaluate that integral without knowing that path a priori. So one way we can get around that is if we can somehow express the concentration, or the time dependence of the concentration of one of them in terms of the concentration of the other one. Then we can substitute that into this expression up here and that'll allow us to solve something. All right, so let's solve for the concentration of B as a function of time. If I do that using this relationship here, what I would find is that it's equal to B at time 0 minus A at time 0 plus A at time t. Now, all I've done is algebraically solve for B of t over here. Okay, but now I can plug this in for B in this rate equation. So now I'll have a rate equation that looks something like this. Is equal to K times concentration of A times a big expression B0 minus A0 plus A. All right, now we could be carrying a lot of baggage around with this, so what I want to do is I want to rewrite this using x as my action variable here. So in other words, I'm going to have minus dx dt is equal to k times x, and then I'm going to arbitrarily let this pair of constants be equal to some other constant. I'll just call it little a. It doesn't really matter what we use. But I'll have k times a plus x. So now I can clearly see that this is an equation, a differential, that I can separate the variables. I can divide both sides by this, and I can multiply both sides by this, and I'll end up with the equation dx over x times a plus x. So now all of this depends only on x is equal to k times dt. And all of this only depends on time. So this part I know I can integrate that pretty easy. I'm not going to worry about that too much. It's just going to give me kt. What about all this other stuff? Okay, well, I'll point out that when you have a function that looks like this and you need to integrate it, I'm not going to give you a math lesson here, but the way you typically do this is you divide this into two partial fractions. You solve for c and d so that c times this plus d times that gives you 1. You solve for c and d. It turns out that in this case c is going to be equal to 1 over a and d is going to equal minus 1 over a, and that will give you this right answer. So when I'm integrating this side for this reaction, I'm integrating from, for example, my initial value of a to my value of a at times t, negative sign in front, and I'm going to have, whoops, let's make it dx divided by x, and it's times c, which is 1 over a, so it'll be divided by by a times x. And then I'll also have minus dx over a times a plus x. All right, so these are the integrals that I have to actually evaluate, and probably I've given you more math than you wanted to see, but I wanted to show you that this is not an impossible integral to do. In fact, it's quite straightforward. And in fact, when I do evaluate it over these limits, I get actually a fairly tidy result. Now, once I integrate over these limits, I'm also going to have to go back and use my definition for b. Okay, and the reason for doing that is to simplify the expression that I get in the end. But the expression that I'll get from performing these various operations is that my, the right-hand side of the equation, which is kt, is going to be equal to 1 over, and it's going to be this difference, a0 minus b0, times the logarithm of this set of, I'll have a at time t times b at time 0 divided by a at time 0 and b at time t. And so this becomes the integrated rate law for this reaction. All right, now I'm not so interested in your being able to always figure this out, but what I want to show you is that when you have two reactants, it's not as simple as just doing a simple integral like we've been doing for first, zeroth, and second order rate laws. It's actually a more involved process where we first have to express the second reactant in terms of the first reactant. We then need to substitute that into our rate law as written up here. We need to rearrange so that we can separate the variables, which we have done here. And then when we integrate, we can reconstitute everything and get a final integrated rate law that tells us how these two things vary as a function of time, and they're not independent of one another. All right, so that's the bottom line, is that these two things are varying with time, not independently, but codependently on one another, as you would expect in a chemical reaction.